sort of swap out the entire state of the processor, or the entire operating system visible state of the processor, to this memory page, swap in basically the state of a new VM or the hypervisor. And so it's sort of like the sort of old page swapping, or like segment swapping memory techniques. And what it basically does is, once you have the guest OS running, you configure sort of a set of events that are interesting. And once these events are what cause VM exits and pass control back to the hypervisor. And basically, the point of this is that you want to keep for speed, you want to keep the guest OS running as often as possible. If you're only running one of them, as I do, basically, I try and never have the VM ever exit unless absolutely necessary, so you don't notice the speed hit. And basically, just carve off a memory page, and that's where all the state is held. Where are we actually seeing this? I forgot to put on mainframe stuff that is so beyond my time it's not even funny. And I generally I have a short view of history. To me, mainframes didn't exist. Basically, VMS was the first operating system. Once there was virtual memory and multitasking, then computers actually existed in my mind. Mainframes are just the stuff in college textbooks that they felt they had to talk about, but no one really cared. Or at least I didn't, because I was a punk like that. So IBM obviously was able to take this technology that they had invented in this prehistoric time that I don't acknowledge really existed, and use that on their IBM on the power processors. And so they have logical partitioning, which I actually never got to play with because it's really expensive to get the software to do it. They'll give you the hardware that's capable of doing it, but the software to manage it, they cost way more, and you need a separate box for it. Big pain in the butt. The Intel and AMD solutions, much easier to use. They're in your processors now. If you have a MacBook, Intel VT is in the Core Duo, Core Solos. So if you've heard of Parallels Workstation, basically the reason they were able to implement this so fast is because they didn't have to go through all the work that VMware did of binary translation and all this stuff. It's really complex. They just use the VT instructions, and their hypervisor is so much smaller than the code that VMware had to do to support older processors. And basically, so VTX is the virtualization for x86, and that's been shipping since January 2006. Intel also has VTI, which is virtualization technology for their mythical Itanium processors, another thing I've heard of, but I've never actually seen. And that's supposed to be coming out sometime soon. And AMD has basically a essentially isomorphic instruction set in their AMD 64 processors, and those are shipping June 2006. You have to ask Joanna. She knows AMD. I don't. Is it June? End of May. Okay. All right. Another transition. So let's talk about how the virtual machine extensions actually look and work. Intel introduced two modes of operation for the processor for Ring 0. Basically, there's VMX root, VMX non-root. Oh, and just to make things really confusing, I'm going to follow Intel's lead and just use terminology interchangeably from VTX, VMX, or before they called it Vanderpool. So the official marketing name now is VTX. It's Virtual Technology Extensions, or Virtualization Technology for x86. Basically, when they were designing this, they called it virtual machine extensions. So all the instructions use VMX. A lot of the terminology uses VMX. So I'll just try and make it as confusing as possible. So like I said before, Ring 0 is now split into two operating modes, VMX root and VMX non-root. VMX root, fully privileged. Everything operates just as you assumed. Non-root is basically where VMs are run, and they can run basically even privilege instructions without a problem. There's just a small list of basically privilege instructions and privilege operations that cause a VM exit, and control gets passed back to the VMX root mode, which is where the VMM hypervisor lives, and then basically it handles the event. And it'll emulate an update to the page table. It'll do whatever it needs to basically virtualize certain things of how the guest OS runs. yeah, so here's a list of things that cause what's called a VM exit. This is the transition from a non-root to VMX non-root to VMX root mode. Basically, you can set a list of exceptions that you're interested in. So basically, anytime there's a access violation or a page fault, a protection fault or a page fault, you can be notified and handle it there, or you can just let the OS handle it and then get notified on the double fault that the guest OS is completely hosed at that point. You have what's called an I/O bitmap, where you can basically, over the I/O space, you can selectively say which device accesses you want to be notified about. So if you want to, virtualize the entire environment, you say, I want to be notified about every device access. So anytime the guest OS accesses a device, causes a VM exit, and basically the I/O request is passed to a virtualized device. However, this can be kind of slow, and you can decide that, well, I'm just going to let keyboard interrupts go straight through because I really could care less. And so you can mark that out of the bitmap, and then basically for every keystroke, you're not swapping the guest OS out back to the hypervisor and back again, and you have increased performance. Or you can also do what I do, and I just say, what, I don't really care about any device access. Why don't you just let it access everything? And basically, I can only say, but when it accesses the disk, I'd like to know about that. And so that basically, I don't have to write device drivers. The operating system just keeps running with native I/O access. Which, when I was reading the spec, and I saw that device access went straight through, I was like, ooh, this will make like a hypervisor rootkit very easy because I don't have to know or care about devices, and I just let the OS keep doing its thing. And basically, whenever a VM exit happens, the VMX non-root state is swapped out, and the VMX root state is swapped in, much like the cool cube transition that Keynote does. So how does Intel do this? They basically added 10 new instructions and basically a data structure called the virtual machine control structure. And like I said earlier, the VMCS just contains all the OS visible state of the processor. So we have, we have the control registers, debug registers, instruction pointer, stack pointer, flags, all the, basically all the segment registers, and basically, and a selected list of machine status registers. Interestingly, they didn't include general purpose registers, so you actually have to do that yourself. So when you swap in, basically you have the EAX, EBX, ECX of the guest OS, and you have to save that yourself, which is kind of a pain in the butt. And instruction set is really small. You have instructions to enable and disable VMX operation. Basically stuff to operate on the VMCS region, and because this state is pretty quickly transitioned in and out, you can only have one active virtual machine VMCS. You need to select, this is the active VMCS, operate on it, launch it, resume it, and then if you're running more than one VM, you have to swap that, a VMCS for each one in and out. Actually, one thing I should have mentioned with the things that cause I/O or VM exits, you can also, tell the VM to exit on the halt instruction. And basically, most operating systems execute the halt instruction in their idle loop. So whenever the OS is idle, you can say, exit the VM and I'll run another OS. And that's a way you can multitask between VMs and, with good performance. The last instruction is VM call. This is just a general purpose, basically up call from a virtual machine into the VMM. And you can see, this could be used for things like cut and paste between guest VMs and the host OS, file transfer, a lot of, just the general sort of, nice user interface features that VMware does. They have a little instruction that can do that, and you can define your own codes and do whatever you need. What makes VTX interesting is that the entire OS visible state is swapped in and out of memory, and basically makes it fast, makes it easy, and makes allows you to sort of do virtual machine, like save all the OS state to disk, resume the VM later, stuff like that. And like I said, that it allows for direct memory and device access. And so this allows us to do fun things like migrate OSs into VMs on the fly, because after the transition, nothing has changed to them. If they're not aware of virtual machine operation, of like detecting that they're in non-root or root, they have no clue that nothing has changed. They have no way to detect that. And interesting thing in the spec is that some level of detection prevention was a design goal. There's a quote in there. There's no deterministic way, or sort of software visible bit, or just flag to check that'll let a guest know that they're in a VM. And they actually say, you want to allow the host, like the host OS or the VMM, to make it a little hard to know that it's being virtualized. This is, for like say you're running VMs for like a honeypot, things like this. You want to make it harder for an attacker to know they're in a honeypot. So what could we use VTX for? Basically, you can install a hypervisor around your real OS, and basically just use a lot of the virtualization instructions for fast sleep and resume. Basically, you can use it for remote kernel debugging, because you can now debug the entire kernel. Like at least OS X uses basically task switches for kernel debugging, and which allows you to sort of switch out of the kernel whenever there's a panic. But if something in that mechanism is broken, it's really hard to debug that, because in that code they need to implement device access, because you're doing remote debugging over an Ethernet cable. And if there's something broken in that device driver, it's kind of hard to debug. But if you run the entire OS in a VM, you can basically write a debugging hypervisor that allows you to really examine what's going on, and write another driver there, and just keep going back layer after layer after layer. You can also, like, another thing that looks kind of cool, basically you can do like OS checkpoints, because you can have all that state, you can serialize it instantly. You can basically take a checkpoint, some point in the future, take another checkpoint, go back and forth like VMware does with snapshots. And I really wanted this while I was doing some driver development, because kernel panics are a pain in the butt, and it's nice to be able to say it'll just fault, and then I can just rewind back to where I was and be done with it, which is why I do a lot of exploit dev in VMware, because I can get everything set up, launch the exploit, see where it failed, hit revert, do it again, not have to set up the machine, or reboot, like if if LSAS dies. Other thing we can use it for, and the reason like why I'm here is you can make rootkits out of it. And that brings us to my rootkit that I call Vitriol. Not the first. There's a number of other virtual machine rootkits. There's a paper out of UMich and Microsoft Research on something called Subvert, and basically this was introduced the idea, but they used software virtual machines, and they modified the boot sequence basically to load the original OS inside virtual PC. So they basically showed the idea that malware can do this and virtualize the running operating system, and then you have to detect that you're in it, and it's harder to break out of that. There's mine. Joanna is speaking as well today about her rootkit called Blue Pill. She also presented at SysCan.